this talk. This is about a tool that we have developed at the AT&T Center for Internet Research. And it's called TBIT. It's the TCP Behavior Identification Tool. It's a joint work between myself and Floyd, and our other colleagues at AT&T have also contributed to it. The outline of the talk is I'll begin by describing the motivation. Why do we need a tool to identify TCP behavior, or why do we need to do this at all? Followed by that, I'll briefly describe the tool. I'll describe some of the anomalies we have found in current vendor TCP implementations. I'll conclude by describing our future work. So, TCP handles majority of today's internet traffic. People report all kinds of numbers, 90%, 95%. So understanding TCP behavior is clearly important. It's obviously important for OS vendors. They need to improve their performance of their TCP stacks. It's also important for ISPs because a lot of their traffic is being controlled by this protocol, so understanding its behavior is clearly important. There are many documents, various RFCs, internet drafts, and so on and so forth, that specify how TCP should behave. But of course, implementations don't always match specifications, partly by design, partly because of implementation, coding bugs, and all kinds of things. So it is essential that we understand what is the difference between what the RFCs say that the TCP should do and what various TCPs actually do. Here is a quick example. The initial window that is used by a TCP connection is the amount of data, just giving a simple description here, amount of data it sends out in a burst before it receives any acknowledgement. So for example, when a web server gets a request, it is allowed to send out a certain amount of data before the receiver sends any ACKs. Okay? There is an RFC about this, 2414, which gives you this formula that shows how the initial window is to be calculated for a given MSS. So if you assume an MSS of 512, which is a normal MSS, a TCP implementation is allowed to send a burst of about 2,000 bytes. But we have found using TBIT that there are TCPs out there. For example, this stack that's running on www.uwm.edu that sends 8,000 plus bytes with MSS of 12. And just for fun, we tried an MSS of 100, and we found that this web server will send a burst of 80 packets without receiving a single ACK. Okay, and this large such large burst of packets clearly mean buffering problems, loss, delays. So it's important to see what TCPs that are out there that actually they do. Okay. Now, how do you detect misbehaving TCPs? So there are two ways of doing it. One is passive detection. One Paxson in 96 and 97 basically carried out thousands and thousands of TCP transfers across nodes that were spread all over the internet. And he looked at the TCP dump traces that resulted and found several anomalies. He wrote a couple papers about that. I think he also gave a talk here at NANOG. But such passive detection has its limitations. For example, you want to figure out how a particular TCP implementation behaves when, say, for example, SYN-ACK is lost. Okay? Now, you're going to have to keep on doing this until you actually get a TCP dump trace in which SYN-ACK is lost, and then you see what happens. Okay? So that's kind of time-consuming. So TBIT is a tool that actively probes TCP stacks at various web servers, okay, to test the behavior. Here is an example. Now, the basic idea is like this. You basically send fabricated TCP packets over raw IP sockets, so you need root permission. Okay? So, for example, you send a SYN, and then you erect a host firewall that will prevent the kernel from seeing the SYN-ACK that comes back. Okay? Otherwise, the kernel will say ACK for a packet it never sent, it will send a reset, and your test will be doomed right there. Okay? At the same time, the BPF device will deliver this block packet up to the user process that sends the SYN packet, and now you can respond to it in any way you want. So in net effect, what we have is a user-level, user-controllable TCP without any kernel changes. Okay? So this work is based on the Sting project that was done at the University of Washington by Stephen Savage. So as an example, for example, I mentioned the initial window, and I'll keep using this as a running example. Okay? How do you determine what initial window a web server is using? Okay? So you send the SYN, you receive the SYN-ACK back. Okay? Now you have established a connection. You send an HTTP GET request, okay, for the basic document, and you don't ACK any incoming packets. Okay? You wait, since you're not ACKing any of the packets that are coming in. After some time, the TCP stack at the web server will retransmit the first packet. At this point, you terminate the test, and then the initial window is the maximum sequence number you have seen. Okay? And you can check this with several MSS values. Since it's a completely user controllable TCP, you can set whatever MSS you want, and this will let you figure out whether it behaves differently with different MSS sites. Okay, so this is an example of how things are done. We have implemented many such tests. So, for example, and of course, this is not all as simple as it sounds, and there are several difficulties, and I'll come back to them at the end of the presentation. We have implemented several tests so far. Some of them are handshake tests, whether how many TCPs that are out there that, for example, use timestamps. How many TCPs are SAC capable? How do TCPs respond to congestion or packet drops? Do they reduce their congestion window? Which exact flavor of congestion algorithm they use? NewReno, Reno, Tahoe. There have been several proposed things. Selective acknowledgements. Do the clients, the web servers construct SACs correctly? When a client sends SACs, do they respond to SACs correctly? I mean, most of the major OSs that are out there, Linux, for example, and Windows 2000, they provide selective acknowledgement, and we want to see whether this is being used effectively. There are other tests, for example, what is the initial window that we saw, whether there are any TCP implementations that are out there that handle ECN correctly. Okay. So I'm going to present some results now, and the background for these results is we had two lists of web servers. Okay, one we just got from 100hot.com, and I will call this list the hot list. We are not claiming that these lists are representative in any way. This is just something we got off the web. It has 200 unique IP addresses. We then got a trace from an ISP proxy. It was given to us by Dax Gelson. And it has about 27,000 unique IP addresses of web servers. We repeated the test at least twice, each test that I'm going to report on. And we are going to report the results only if the results are consistent across the runs. And I'll describe later why this is important. Our ISP, which is essentially UC Berkeley, it does not allow us to run Nmap. So we do not have any correlation of what anomalies we saw in the TCP with what OSs they run. Whatever information we have, it has come simply because people gave it to us voluntarily. If any one of you is willing to give me an account and I can run Nmap, then please let me know. The initial window that I described, we ran about 638 tests from the ISP proxy list that we had. And as I said, we found 4 hosts that will pump out 8,000 bytes without ever waiting for an acknowledgement. So that comes out to about 17 packets with MSS of 512, about 80 packets with MSS of 100. And there were several, these are the people who do it. We found that there are about 12% of the hosts use initial windows of more than 4 packets, which is a violation of what's required by the RFC. Okay. Timestamps. Timestamps enable TCPs to better estimate the retransmission timeout value, and this is essential to improve TCP's performance. We used about 136 tests from the hot list, and we found that 25% of the servers do not use timestamps. And there are some notables in this list, for example, eBay.com, HP.com. Okay. We also found that IBM hosts, under certain circumstances, AIX hosts, send garbage in the timestamp option. We reported this problem to IBM, and the fix is in the works. They said that they couldn't do it before the Olympics was over, so hopefully they are going to do it now. We have not tested if timestamps are used correctly. That's a whole different area, and whether the wrapped sequence numbers are done correctly and things like that. We haven't checked that yet. Okay. Congestion window reduction. So TCPs are expected to cut their sending rate in half, okay, when on each packet drop, and this is essential to the stability of the internet. That TCPs reduce their sending rate when they encounter congestion, which they find out by experiencing a packet drop. Okay, we ran about 6,000 odd tests from the proxy list, and the way we did this was we let the sender window reach about 8 packets, and then we dropped 1 packet. From that point onwards, we counted all the outstanding packets, and that told us whether the host reduced its congestion window correctly. Okay, I'm happy to say that about 99% of the hosts on our list did reduce their congestion window properly. Okay, but there were about 72 hosts, okay, for example, the ones at adobe.com and zdnet.com, they did not reduce their congestion window. They went from 8 to 7, which seems to be kind of strange. On the other hand, there is a caveat here. I ran this test with MSS of 100 because I wanted to make sure that I have enough packets to do this test, okay? And I'm not sure whether that influences the behavior. So we are going to work with this more and see what exactly happens. Here is a quick plot to see how we did this test. So on the right-hand side, you have the 12c4.com plot, okay, where the window was correctly reduced. Now look at the first dark packet which we dropped, around 0.6 seconds, okay, from a window of about 8 packets that were coming back, okay. So the x-axis is time, the y-axis is the highest byte carried in the packet. So we dropped the 8th packet, okay, and as you can see, it sent 4 packets without getting any further acts so basically what that means is that it reduced its congestion window at that point from 8 to 4, okay. The other graph on the other side, you can see that after the first packet was dropped, it sent about 7 packets. So that's incorrect behavior, okay. So this is what we have found, and it would be interesting to see what OS this is, why they are doing this, whether this has got anything to do with the MSS that we are using and things like that. Okay. Selective acknowledgements. Selective acknowledgements are now available through most major operating systems. Linux, I think, all versions of Linux, most of the versions of Linux that are out there. Windows 2000, Windows 98. I don't know about Windows 95. So we ran about 136 tests from the hot list, and we found that 42% of major hosts that are out there, they're not SAC capable. So, for example, Netscape.com, CNN.com, none of them run SAC. And of course, SAC is a bidirectional thing in the sense that both client and the server have to be able to do it before it takes effect. Okay. What's worse is that many of these SAC capable hosts, the 58% hosts that actually do claim that they do SAC, they don't seem to do it correctly. So we'll see how. Okay. So we ran about 2,000 tests from the proxy list to see whether the SAC is used correctly. And the test was like this. We let the window reach 8 packets, and we dropped the 6th and the 8th packet. Now, if SAC is implemented correctly, as it should, as the RFC says, okay, then they should be retransmitted together. But if it's doing the default NewReno or Reno behavior, then you will see only retransmission of 6, which is sort of a degrading in the performance, okay? And this was a very surprising result. We found that only about 6% of the hosts on our test did the SAC correctly. Here is an example. So this is on the again on the x-axis here, the time, y-axis here, the sequence number. One of the graphs shows that the SAC is correctly used. So as you can see, the packet with sequence number 600 and 800, they're dropped, and they're immediately retransmitted right there, and they're both retransmitted together. So that's the correct way the SAC is used, because the sender is able to infer that those 2 packets are lost. On the other hand, if you go to the default NewReno behavior, then SAC info is ignored. Packet 6 is of course retransmitted because of the just because of the cumulative acknowledgement number, but nothing after that gets resent again. Okay. So one of the other tests we implemented was explicit congestion notification. Okay. 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 One of the other tests was explicit congestion notification. This is a new standard. As far as I know, it's available only in Linux 2.4. Okay. And you can, I think the default is that it's disabled. You can set it enabled. So ECN is negotiated in some sense during the SYNAC exchange. Okay. So the TCP that is running on an ECN capable host sends 2 flags, CWR and ECE in its SYN, and the host, the other end, if it's willing to do ECN, it responds by setting ECE flag. Okay. We checked about 26,000 hosts from the proxy list, whether they behave correctly, and what we found was surprising. Most of the time, if these flags are set by the client, the server just ignores them and everything is fine. But 8% of the web servers that are out there, okay, they simply drop any SYN packet that contains CWR or ECE flags, which means if you are a Linux 2.4 user, you enabled ECN because you want to be a good citizen, and suddenly 8% of the web servers out there would be unreachable. The problem, it turns out, at least in some cases, was with some local, Cisco local director. Dax Kelson actually worked more on this, and it's a fix has been posted on some of the news groups of the Cisco website. We don't know if some of the host tags themselves have problem dealing with this flag, but that's the story so far. Okay. TCP flavor. What are the what exact congestion control algorithm that is used by various TCPs that are out there? Whether they use Reno or NewReno or Tahoe. This is when they do not use SAC, and we found that about 61% of them use NewReno, 22% use Reno, and the rest Tahoe. The test for this is somewhat complicated. If you're interested, I'll show a URL where we have a detailed set of results and explanation and how everything works. Okay. Interesting thing is we found that some Microsoft servers, and I literally mean Microsoft servers, www.microsoft.com, we found that they took timeout on every packet loss for small transfers. So we talked to people at Microsoft, and they found a bug, and apparently a fix is in the works in the next version of Windows 2000 or Service Pack, something like that. So I'm just going to skip this graph here. Okay. There are several difficulties when doing this test. Okay. For example, as we saw, to test whether the server runs SAC correctly, you need at least 14 packets. Okay. Now, if you want to run it against any arbitrary web server, the only page you can be sure of that the web server will deliver is the root page. Okay. And this might not be large enough to give enough packets to do the test. So maybe we can use smaller MSF. But does this create other problems? Do web servers respond to different size segments differently? They shouldn't, but maybe some of the results we have seen could be artifacts of that. So we are working more on that. If packets are lost at random places while we are conducting the test, then our results might be incorrect. And the only protection we have against it is we run the test multiple times and hope for the best. Look at the graphs also, of course. So you can have multiple hosts answering the same IP address sitting behind some kind of a TCP sprayer or something. This might give non-repeatable results, and I'm not sure how to handle this actually. And we do not, of course, know any easy way to test without a web server. It would be nice if everybody ran some kind of a TCP data sender and some kind of a TCP data sync, but of course nobody will do that. So future work, we intend to extend this tool as sort of a full conformance checker for TCP. It would be nice to use this to generate automatic simulator models so people can test their TCPs in a simulation environment. We plan to extend this approach to investigate other behaviors of internet infrastructure. I would love to get more suggestions from the audience what we can do. For example, some kind of DNS testing. And we would at some point of time, if we find, run nmap so that we can present these results in correlation with what OSs they are. And finally, all the source code, detailed results, and a draft report are available. People are welcome to download the source code, play with it, modify it, and please let us know what you think. Thank you very much. Do you have any questions?
Well, have you looked at offered window sizes from TCP servers, from web servers?
Offered window sizes?
Yes, I mean the maximum window size supported.
No, that we have not looked at that, but that would be definitely an interesting thing to look at. Yes,
because I have noted that even large high bandwidth streaming content, like Christy Aguilera video clip at 1 megabit per second or so, gets offered on servers with very low window sizes, so that the theoretical reach of those is pretty limited. I mean, it cannot be received correctly unless you're 50 milliseconds from the server or so.
That's definitely something we would like to look at. Thanks. Okay.
So we had one. Oops, too close. We had one more question of this audience, which is that we want to run Nmap because we want to be able to identify easily what OS has what TCP behavior, and when we identify it, we talk to the person who we know who wrote the TCP for that OS, and they fix it. How many people here think that's socially irresponsible and we shouldn't run Nmap for that purpose, and how many people here think it is okay? And first, the hands of people who think it is okay to run Nmap. Nmap is a tool used by hackers. That's what it's mostly used for. So most ISPs won't let you run it, and most web servers treat it as a hostile act. And it's just on the web, someone wrote it. And one of the things that it does is it looks at peculiarities of TCP behavior, what kind of options are exchanged, to make a guess about what the OS is. It also does some stuff which is port scanning, which we don't do when we run it, which is the most hostile part of what Nmap does. So that's why people wouldn't like it. That's why web servers wouldn't like Nmap. People running web servers wouldn't like Nmap to be run. They sometimes send you mail saying, "Oh, you're running Nmap against our site. Why are you doing that?" And we send mail back saying, "Well, you know, because it's research," and they usually say, "Okay." But
one quick suggestion about that: there's a gentleman, and I'm sorry I forget his name, but he walks the DNS tree, checking for, the same kind of, is DNS configured properly? Different zones? Is EDDR.ARPA set up and so forth? And he posts something to major lists like, the NANOG list and INET Access, maybe, some of the ISP lists that Sparky runs, and just lets people know ahead of time that he's going to be doing that. Of course, with DNS, the issue is, he wants to do zone transfers to check the data, and if you don't open up your zone for him to transfer it, he can't check your data. If you were to post something just to let folks know you're doing it ahead of time so they can be on the lookout for it and know, when they see it, that, who it is and who's responsible, that would probably go a long way toward, eliminating some of those problems.
Actually, there's a simpler solution. Nmap will generally make a lot. You'll end up with a lot of complaints if you're using Nmap.
We can't hear you. Can you please?
You'll end up with a lot of complaints if you use Nmap. It's probably a bad idea. You probably should use a search engine. Since you're testing primarily web servers, just get a little search engine. There's lots of different publicly available ones. Use that to crawl to get all kinds of links. You'll end up with all kinds of different web servers, and you can use those for testing. And since all you're making is HTTP requests to things that are already publicly available, you'll avoid getting complaints. But if you use Nmap, that's a really bad idea.
Okay, so we have both sides of the opinion. Okay.
do you want to get my
Sure.
address up?
Sure.
If you use Nmap, you'll end up with queries from people like NASA and whatnot that say that they're part of a federal information system, and they're saying that they have to look into every potential security, incident.
Yeah.
So
you're right.
Yeah.
So yeah, the couple of times we ran Nmap just to test things, we did get queries from the target of the Nmap scan, and most of the times they were nice after we told them that, hey, we were just, this is what we are doing. Except that at some point of time, the people who run the Berkeley network started saying, well, sorry, you're not going to run that anymore. So that's the idea.
I refer to these as goobers with firewalls, and there's a lot of personal firewall technology out there, and people don't know how to interpret the results. So since I run a root name server, I often am told that I am attacking them by sending them UDP port 53 packets. And since I host a box for KC as part of the Skitter project, I also receive all sorts of hate mail from people who don't understand why I'm pinging them. So I'm already immune to reports from NASA as to how bad I'm being, and if you'd like a guest account on ISC's shell server to run Nmap, you're quite welcome to.
Oh, thank you very much.